This lesson helps you understand the set of real numbers used in algebra. When you multiply a number by itself, you get the square of the number. For example, 2 squared is 4, and 3 squared is 9. So you can say 4 is the square of 2, and 9 is the square of 3. You can turn this around and say 2 is the square root of 4, and 3 is the square root of 9. In general, a is the square root of b if a squared equals b. So 2 is the square root of 4 because 2 squared equals 4. And 3 is the square root of 9 because 3 squared equals 9. This symbol represents the positive or principal square root of a number. It's called a radical sign. The expression is a radical expression, and the expression under the radical sign is called the radicand. A set is a well-defined group of objects. The objects in the set are called its elements. You can represent a set in roster notation by listing the elements in the set within braces. Variable names for sets are usually capital letters. Notice for these sets, all of the elements of set B are also in set A, the numbers 1 and 2. So we can say B is a subset of A with this expression. The relationship can also be represented by this Venn diagram. Notice set B is drawn completely within set A. The most basic set of numbers in algebra is the set of natural numbers. These are the set of numbers you count with every day, beginning with 1, 2, 3, and so on. Since the elements of this set are infinite in number, only the first few are listed, followed by an ellipsis, these 3 small dots, which means to continue the pattern. If you combine the natural numbers with the number 0, you have the set of whole numbers. If you combine the set of whole numbers with their inverses or negatives, you have the set of integers. Finally, the set of rational numbers is a set of numbers that can be written as the ratio of 2 integers, a over b, where b, the denominator, can't equal 0. Division by 0 is not defined in algebra. Rational numbers are the set of numbers you use every day, including fractions like 1/2 and -7 over 9. Integers are also rational numbers. For example, the integer -2 can be written as the ratio of -2 over 1, or -10 over 5. Decimals are also rational numbers, since a decimal like 0.3 can be written as the ratio of 3 over 10. Finally, 0 is a rational number, since 0 can be written as the ratio of 0 over 3, or 0 over any integer. Here is a Venn diagram that shows the relationship between these sets of numbers. The natural numbers are a subset of the whole numbers. The whole numbers are a subset of the integers, and the integers are a subset of the rational numbers. There's another set of numbers you may not know about. Irrational numbers are numbers that can't be written as the ratio of 2 integers. Irrational numbers can be defined and described, but they can't be written down with the digits we use for rational numbers. If you've studied geometry, you're familiar with the number pi, defined as the circumference of a circle divided by its diameter. Approximate values of pi can be written down with digits, but never the exact value. So 3.14159 is a rational number whose value is very close to pi. However, this symbol represents the irrational number that's exactly equal to pi. Since you can't use digits to represent irrational numbers, you have to use symbols. Another example of irrational numbers are the square roots of numbers that aren't perfect squares, like the square root of 2. This is easy to prove. Assume for a moment that the square root of 2 is rational. Let the square root of 2 be a rational number n. Then by definition, n squared must be equal to 2. Next, notice on the number line below, the square root of 1 is equal to 1, and the square root of 4 is equal to 2, which means the square root of 2 must be a number between 1 and 2. So the square root of 2, the number n, must be a fraction. And when you square a fraction, you get another fraction. But this contradicts the statement that n squared is an integer. Since the assumption that the square root of 2 is rational leads to a contradiction, the assumption is false, and the square root of 2 is not rational. So the opposite must be true. The square root of 2 must be irrational, and the proof is complete. This proof is simple but subtle. It's called proof by contradiction. It's hard to understand the first time you see it. You may have to think about it for a while. If you pick up your calculator, it's programmed with a method for estimating the value of the square root of 2, which is about 1.414. And if you square 1.414, you get 1.999396, which is very close to 2. So 1.414 is a rational number whose value is very close to the square root of 2. However, this symbol represents the irrational number that's exactly equal to the square root of 2. Right now, you may not understand everything about irrational numbers, but it's important that you know they exist. So if you take the set of rational numbers and the set of irrational numbers, together they form the set of real numbers. Finally, real numbers can be represented on a number line. A number line is usually drawn with the 0 point of the line in the middle called the origin. Points to the right of the origin represent numbers that are positive. Points to the left represent numbers that are negative. For any point on the number line, points to the right represent numbers that are larger. Points to the left represent numbers that are smaller. Even when only a few of the integer points on the number line are labeled, the number line includes all the infinite number of rational and irrational numbers between the integers. Finally, there is a one-to-one mapping between the set of real numbers and points on the number line. What this means, any of the infinite number of points on the number line is represented by some real number. And any of the infinite number of rational or irrational numbers is represented by a point somewhere on the number line. This lesson helped you understand the set of real numbers used in algebra. And this lesson was brought to you by the Math Fun Academy. Its continuing mission: to explore strange new worlds, to seek out new math and new equations, to boldly go where no math student has gone before.